In this video, we're going to start our discussion of Chapter 5, Systems of Linear Equations. So we're going to start with the mathematical background and then go through solving systems of linear equations with elimination methods, and then we'll go through iterative methods to solve linear systems. So in this video, we're just going to focus on the mathematical background and just go through the first half of the mathematical background. So topics in linear algebra form the core of numerical analysis. Many engineering problems require at some stage the solution of a system, and often a large system, of algebraic equations. In fact, MATLAB, the name, comes from Matrix Laboratory, was conceived as a collection of tools to aid in the analysis of linear systems and was derived from a well-known set of linear algebra routines from Fortran. So in Chapter 4, we determined the value of x that satisfied a single equation, f of x equals 0. Now we want to deal with the case of determining all of the values x1, x2, up to xn that simultaneously satisfy a set of equations. And these equations can be of the form f1 of x1, x2 up to xn equals 0, f2 of x1, x2 up to xn equals 0, up to fn of x1, x2 up to xn equals 0. So we have these n functions of n variables, all of the form f of the variables equals 0. We want to find the values of x that make all of these equations satisfied at the same time. So these systems can either be linear or nonlinear. In this chapter, we're going to deal with linear algebraic equations that are of the general form shown here. So a11x1 plus a12x2 up to a1n xn equals b1. And this can be repeated to an1x1 plus an2x2 up to ann xn equals bn. So all of these equations are linear combinations of the variables x1, x2 up to xn. So they're linear equations and written in this general form. Here the a's are constant coefficients and the b's are constants, and n is the number of equations. So we can introduce this idea of a linear vector space and talk a little bit about what this means. So a linear vector space, as a non-rigorous definition, is a set that is closed under addition and multiplication by a scalar. So for example, the set of real numbers is a linear vector space. So if I take any two real numbers and I add them, then I will get another real number. So if I take the number 1 and the number 3, those are both in this vector space R. If I add them, I'm going to get another number that is also in the same vector space R. So this means that it's closed under addition. If I take any real number and I multiply it by a scalar, then I will get another real number. So I have an element of my vector space 5, and I'm going to multiply that by a scalar, square root of 3, and what I end up with is another element of that same vector space R. So this means that it's closed under multiplication by a scalar. So this basically what that means that it's closed is that when I take an element of the set and I multiply it by a scalar, I'm still left with another element of the same set. In general, in this course, we're going to consider a linear vector space as the set Rn, which is basically R times R times R up to n times. So an element of the set is basically a vector that has n elements, so x1, x2 up to xn, where each of those elements, x1, x2 up to xn, is a real number. So the dimension of this vector space is n, and a vector in this space, so x in Rn, has n components, x1, x2, xn, each of which is a real number, as we said. And the zero vector is the vector in the space whose components are all equal to 0. So for example, we can consider R2. So if n is equal to 2, we have R2 can be represented as R by R, and each element of R2 has two components, for example, x1 and x2, and each of those x1 and x2 are real numbers. So this is kind of graphically how we represent an element in R2. So for example, this vector u has two components, u1 and u2, and each u1 and u2 are real numbers that are the coefficients, and E1 and E2 are the vectors that describe kind of the principal directions. So we can represent the vector u as this combination u1 e1 plus u2 e2. Similarly in R3, each element in R3 has three components, x1, x2, x3, and then each of those x1, x2, x3 are in R, so they're real numbers. So this is how a graphical description of how we of what a vector in R3 looks like. So U has these three components, U1, E1 plus U2, E2 plus U3, E3. And the zero vector, as we said, is the vector in a particular space that has all of its elements equal to 0. So in R, x is equal to 0 is the zero vector. In R2, x is equal to 0, 0 is the zero vector. So again, we've got R2, so we've got two elements. In R3, x is equal to 0, 0, 0 is the zero vector. And in Rn, x is equal to all zeros with a length n is the zero vector. So let's talk about the norm of a vector. Vector spaces can have a function called the norm, which is used to describe the size of vectors, and it assigns strictly positive values for non-zero vectors. There are many different norm functions that can be defined, and the Euclidean norm is by far the most commonly used norm function, and it's the one that you're probably familiar with, and it's defined as shown here. So if we've got for every vector v in my space Rn, the norm of v is given by the square root of the sum of the squares of all of the components of v. So the square root of v1 squared plus v2 squared up to vn squared. So that is the form of the Euclidean norm. And it tells me how big is v. Related to this, we can talk about the Euclidean distance. So if we have two vectors, x and y, in our vector space Rn, the distance, the Euclidean distance between these vectors is the norm of the difference. So I take x minus y, and then I take the norm of that. It's the square root of x1 minus y1 squared plus x2 minus y2 squared up to xn minus yn squared. So the Euclidean distance is used to check whether two vectors are the same or not. And this will be useful when we're talking about convergence of a method. We want to check how close two vectors are. So for example, if I have x and y defined here, this would be in R4. We take the difference, x minus y, is 0.1, 0.1, 0.05, and 0.01, and then we take the norm of that. And that tells us how close x and y are to each other. So if this norm is 0, then x and y are equal to each other. So now we know what vector spaces are. So we can talk about linear functions between vector spaces. So if we're given a linear vector space V and another linear vector space W, then we can define a linear map T, which is a function that goes from V to W, such that for every u and v in V, so for every vector in V and every alpha and beta in R, so scalar values in R, we can write that T of alpha u plus beta v is equal to alpha t of u plus beta t of v. So basically, this just means that the operation is linear. So for example, if we have some alpha in R and we want to define some function, some map that goes from R to R such that f of x is equal to alpha x. So what does this mean? This means that I've got my values of x, and I've got f of x, and if I define this function, my alpha here is equal to 5. So I define this function f of x is equal to 5x. So what it does is it takes a value of x, and it gives me a value of f of x. So and the value that it gives is according to this equation. So if I take 1, I get 5. If I take 2, I get 10. If I take x is equal to 3, then I get 15. If I take x is equal to 4, then I get 20. So what it does is it takes these values of x and it maps them onto these new values f of x. So it maps the values x, so for example 1, 2, 3, to the values of f of x, for example 5, 10, 15, etc. So this just shows exactly the same thing, but we can show it in a slightly different way. So if I've got my first vector space R, which is just my set of real numbers, or the number line, and I use this linear map between the vector spaces, then I can see how each of these numbers is mapped to f of x in my other space R. So the function, again, maps the values of x, so 1, 2, 3, to the values of f of x, 5, 10, 15. And I can also go the other way. So if I take a value here, I can actually find what value that corresponds to over here by using this inverse relationship. So if I have 5, the inverse of f of 5 is 1 over 5 times 5, which gives me 1. Again, I can do the same thing. If I start with 10, I can do this inverse, and I know that I'm going to get 2. So this means that the function is invertible. And if I take the inverse of the original, then I'm back to the original. So basically, I start with x, I go to f of x, and then using this function, and then I can do the inverse operation, and I should get back to exactly where I was in the beginning. So let's look at another example. If I've got a1 and a2 in the set R, and I have this function that goes from R2 to R such that f of x is equal to a1 x1 plus a2 x2. So here x is in R2, so x has two components, x1 and x2. So what we've got here is my space R2, and I've got a bunch of vectors defined in it that have components x1 and x2. So for example, 0, -1, 1, 1, 3, 0, 4, 0. And then I can use this function to map these onto R. So I'm going here from R2 to R, which means that the dimension of my sort of target space is different than the dimension of the space I'm starting in. So here I take any value of x, which has two components, x1, x2, and then I apply my function a1 x1 plus a2 x2. So for example, a1 could be 1 and a2 could be 2. Then my function is 1 times x1 plus 2 times x2, and then I'm going to get some real number r. So for example, if I put the vector 0, -1, I would get that maps onto -2. If I put in 1, 1, then that maps onto +3. If I put 4, 0, that maps onto +4. And if I put 3, 0, that maps also to +3. So now, so this function maps the values x, so for example 1, 1, 4, 0, etc., to the values of f of x, which are 3, 4, etc. So now, can I consider the inverse? So can I take this value and know which vector I end up at? Well, as we saw, 2 of these vectors mapped onto 3. So if I take 3, I don't know which vector I'm going back to. So this means that this process or this map is not invertible. because I cannot uniquely figure out where to go when I'm going back in this sort of inverse direction. So now we can consider this set, A11, A12, A21, A22, as a subset of R. So each of those are real numbers, and a function that goes from R2 to R2, such that this is what my function is defined as. F of x is equal to A11x1 plus A12x2, and A21x1 plus A22x2. So x, again, is in R2, so it has two elements, and it's going to map onto also R2, so my f of x also has two elements, which are given kind of as these two rows here. So we can write this as A11, A12, A21, A21 times x1, x2 in this matrix notation, which we will talk about quite a bit later. So this we can call A, and this we can call x. So what this does is it takes my an element in my space R2 and maps it to a new element in my space R2. And so, for example, if I have A is defined as shown here, where 1, 1, 0, 1, this is what the map looks like. So A takes any vector in R2, and it maps it to a new vector in R2. So if I look at the corresponding colors here, so it takes this green one and it maps it here. It takes this green one and it maps it here. It takes this red one and it maps it here. And you can see these black ones haven't changed. It takes this black one and it maps it here. So if we look at, for example, this black one, this would be defined as 1, 0, and then when I multiply that or apply my map A to that, I end up again with 1, 0. Where here, this green one would be defined as 0, 1, and when I apply my map to that, so for example, if we had 0, 1, what we would end up with is 1, 1, which is what we've got here. So what this matrix representation does is it takes any vector in R2 and maps it to R2. So the matrix represents the list of coefficients of a linear map between vector spaces. So given a linear vector space Rm and another linear vector space Rn, a linear function f that goes from Rm to Rn has the following form for every x in Rm. We can write this set of equations, which we can basically define as this matrix, and then I get it takes any, so here if I put in any x that has dimension m, I get out some vector b that has dimension n, because I'm going from Rm to Rn. So the function x takes a vector x with m components and returns a vector b, which is equal to f of x, which has n components. So again, just rewriting that. Using matrix notation, this can be written in a more convenient form where we put all the coefficients into a matrix, and then we've got our vector x, and we get out our vector b. So we can write this in a compact form as ax is equal to b. So again, a is the matrix, is the coefficients of our function, x is our input vector, and b is our output vector. So a takes x, takes the elements of x, and it maps them into b. So that brings us to a discussion about matrix notation. So there are many different ways to represent matrices and vectors, which you may have seen in some different courses that you've taken. You'll notice that different texts use different notation. So for example, you can use boldface to represent matrices and vectors, and sometimes vectors will also have like this arrow or half arrow or line on top of them. You can use brackets to represent vectors and matrices. So typically you would use square brackets, and sometimes for matrices, and sometimes vectors are represented with curly braces. You can use this mathematical notation with a function defining it as a map between vector spaces, or you can describe the elements of a set. So A is in the set of all the matrices with n dimension, or V is in the set of Rn. So there's lots of different ways to lots of different notation styles to describe matrices and vectors, but they all are equivalent. And in this course, we're going to use this bracket notation primarily. We do, as you've seen, sometimes use these other function notation and elements of a set notation, but for the most part, we will use the bracket notation to describe our matrices and our vectors. So if A represents an n by m matrix, then A subscript ij represents an individual element of this matrix, or a component of the matrix. So we can write our matrix A in this way here with a dimension n by m. And a horizontal set of elements is called a row, like what is highlighted here. A vertical set of elements is called a column, as shown here. And when we look at the components, this Aij, the first subscript designates the row that it is in, and the second subscript designates the column that it's in. So if I want to look at the column that's highlighted, for example, this element is A12. So 1 represents the row that it's in, so it's in the first row, and 2 represents the column that it's in. It's in the second column. Another one would be, here, A2m. Again, 2 represents the row, so it's in the second row, and m represents the column, so it's in the mth column. Matrices that have a row dimension of n equals 1 are called row vectors, and their dimension is 1 by m. So instead of n by m, it's 1 by m. And for simplicity, the first subscript of each element is dropped. So we could write this row vector as b is equal to b1, b2, up to bm. Matrices with column dimension m equals 1 are called column vectors, and their dimension is n by 1. And for simplicity, the second subscript of each element is dropped, so we can write c as c1, c2, up to cn. And it is convenient to employ a notation to distinguish column matrix from other matrices. And one way to do that is to use curly braces, which we will tend to do in this course. So the transpose of a matrix is denoted by the matrix followed by the superscript t. And the transpose is defined as a result of exchanging the rows and columns. So if I have a matrix B, which is equal to the transpose of A, that means the elements Bij are equal to Aj. So I exchange the rows and columns and I get my transpose. And we can show some properties of the transpose that we're not going to go through the derivation of these, but it can be shown that if we have two matrices A and B, that A plus B transpose is equal to A transpose plus B transpose. And if I have, again, these two matrices A and B, A times B transpose is equal to B transpose A transpose. And where this matrix multiplication is going to be defined a little bit later. So this brings us to systems of linear equations. So a system of linear equations seeks the solution x, which is our vector, to the equation ax is equal to b. So in matrix component form, this can be written as shown here. So as we saw, our matrix A has these elements, A11, A12, etc. Our vector X has these elements x1, x2 up to xm, and our vector B has these elements b1, b2 up to bn. That's when A is n by m. So what we're trying to do here is we've got, we want to know this input x that is going to give us the desired output b. So we want to find x that is needed, or input x that is needed in order to achieve the desired output. That's what we want to do when we're solving the system of linear equations. And as we have seen, the system of linear equations is equivalent to this, or this matrix representation that we saw in the previous slide is equivalent to this list of all of these independent linear equations as shown here. And the solution of the system of linear equations is the numerical value of the variables x1, x2 up to xm that would satisfy this set of n equations. So there are three possible scenarios when we're writing a system of linear equations. First, if m is greater than n, then we have more unknown components of our m-dimensional vector x than we have equations. So remember, m was the number of variables that we have, the number of x's, and n is the number of equations. So if m is bigger than n, then we have more unknowns than equations. So this system is called underdetermined, and it results in having many, in fact, infinite possible solutions. So let's see an example with m greater than n. So I've got this system here where my m is equal to 3 and my n is equal to 2. So I've got 3 unknowns and 2 equations. So if I set x3 equal to 1 and then I plug this into my 2 equations, I can solve and find that x2 is equal to -1 and x1 is equal to 2 over 5. So this results in a vector x that's equal to 2 over 5 minus 1, 1, which satisfies my equations. I can instead set x3 equal to 2 and then plug this into my 2 equations, and here I find that I have a different vector x, which is 6 over 5, -3, and 2, that also satisfies my equations. And in fact, if I set x3 equal to any real number alpha, I can solve for x2 and x1 in terms of alpha, and I can find my vector x in terms of alpha that satisfies this, that satisfies my equations. So with too many unknowns, you can achieve the desired output with an infinite combination of the input variables. So there's no unique solution for x that allows me, that would satisfy my equations. There's an infinite number of solutions for x. Scenario 2 is if m is less than n. So n, and the n equations are linearly independent, then we have more equations than we have unknown components of our m-dimensional vector x. So this system is called overdetermined. And this results in having too many restrictions, which prevents us from finding a solution. So let's see an example of m is less than n. So I've got this system here with 2 unknowns, x1 and x2, and 3 equations, which are defined as shown here. So if I consider the first 2 equations, I have x1 plus 3x2 equals 1, and 2x2 is equal to 2. This results in x2 equals 1 and x1 equals -2. Then if I plug those into the third equation, what I get is the result is 3. But from my actual equation here, the result should be 2. So this results in a contradiction. So with too many equations, you can never achieve the desired output, as the extra equations will often lead to contradictions. And this is assuming that there's no repetition in equations. So as we said, that for this to be the case, the equations have to be linearly independent. And scenario 3 is if m equals n, and the n equations are linearly independent, then one unique solution exists. So the matrix A that forms the equation has an inverse, and in this case there exists, what this means is that there exists a matrix A to the power minus 1, which is called A inverse, such that AX equals B can be rearranged to say that X is equal to A inverse times B. So I can find a unique solution for X using this inverse. So let's see an example. We've got m equals n, and the equations are independent. So I've got two equations and two unknowns. So I can write out my equations, x1 plus 3x2 equals 1 and 2x2 equals 2. And this results in x2 equals 1 and x1 equals negative 2. So a unique solution exists. There's no infinite possible solutions, and there's no contradiction. So what if m equals n, but the equations are dependent? In this case, the matrix of coefficients is called singular, and no unique solution exists. So for example, we've got this, this system here. So my matrix is 1, 1, and negative 1, negative 1. So you can see that the top row and the bottom row are essentially the same. They're just, all they differ by is multiplication by negative 1. So if I consider the first equation, x1 plus x2 equals 1, and the second equation says x1 plus x2 equals negative 2. So these cannot both be satisfied at the same time. So this means we have a contradiction. Another example with the same matrix, 1, 1, and negative 1, negative 1, with a different output vector b. The first equation says x1 plus x2 equals 1. And then we can say that x2 is equal to 1 minus x1. And both of these equations give us the same information. So this means that there are infinite possibilities for our solution. So in this case, just to reiterate, that m equals n, but the equations are dependent, so they're not linearly independent. So in this case, the matrix is called singular, and no unique solution exists. We either end up with a contradiction or an infinite number of solutions.